This is a video for Math 120, section number 2.4. We are looking at continuity. So first, I'll remind you that the features that are a problem for limits are jumps, vertical asymptotes, and heavy oscillation. I'll ask you this question on the test. An additional feature that's a problem for continuity is a hole or holes on a graph. So a function f is continuous at a if the limit as x goes to a of f exists, if it's defined at a, and if the limit equals the function value. So a hole in the graph would fail one of these. The first problem here gives us 4 different examples. A rational function, a piecewise, well, 2 piecewise functions, and then the greatest integer here, which basically, remember, the greatest integer of 3.8 would be 3. The greatest integer of negative 3.8 would be negative 4, because it's the biggest integer less than or equal to it. In the first problem, f of 7 is not defined because it would make the denominator 0. And it could either be a hole in the graph or it could go off to infinity. But you can see it's going to be discontinuous because it's not defined when x is equal to 7. F of 0 for problem B is defined, but I know 1 over x to the 4th goes off to infinity, and it's actually positive infinity on both sides. So if you look at the left limit and the right limit, you get positive infinity on both sides. I recommend you put it in your calculator and actually see that it's going off to infinity. But if we looked at the graph at x equals 0, we'd have a spot at y equals 1 where x is 0. In the third one here, we have the first function that we had, and it's trying to decide whether or not putting this 1 is actually filling a hole in, or if it's like part B, where it just put a spot on the graph where things are going off to infinity on both sides. So take a look at the graph and see what's going on there. Now, step functions have infinitely many places where they're undefined. At every integer, they're undefined. So you're just going to go down here and work through the problems as I ask you to. In the part C, you would need to factor, and we'll do a few more of these as we go through the problems. We worked a problem very similar to number 2 in class. You can see there's a whole bunch of discontinuities in a lot of places where the limits fail to exist. We've got into problems in the graph at negative 2, and it's just a hole, so the limits will exist there. At negative 1, we have a jump. At 0, there really isn't a problem for continuity. It's just a corner. There will be a problem for slopes if we're looking at slopes on either side. At 1, we have a jump. At 2, we have a vertical asymptote. So this one has an infinite jump. This one you'll have to click to begin. It's a tutorial exercise. It takes a little bit longer. And number 9, they have 2 composite functions. One is the sine of x, which would be a really nice function if it didn't have an x to the 9th in here. So the x to the 9th makes it do some strange things. But because we have just the sine of x, that's our outside function, the f. That's what they're asking for here. What do we compose? And then they ask you to talk about what happens with that composition. For part B, we have the natural log function, which is not defined for 0 and below. So anywhere what's inside here becomes 0 or below, and it wouldn't become anything below 0 because the lowest thing cosine is a negative 1. But we're going to have a lot of places where this is not defined. So this is just going through there and helping you understand where that would be undefined. For number 4, remember that a root is the same as a 0. So if we look at this, we could find the roots. So putting this in our calculator, in y equals, and then graph. So zoom 6 is what I'll do. That gives me my standard grid. I can see that there's a 0 here. If I look at second calc, see the 0? That's 2. And I can see the 0 is between 0 and 2, so I can just type in 0 and 2, and it's going to give me, I'm looking for the 0 in between 0 and 2. So if I do a guess of 2, that's fine. Then I get the zeros at 0.84847. Now, this gives us a perfect setup to talk about the intermediate value theorem. And it says that if f is continuous on the closed interval from a to b, and let n be any number between f of a and f of b, So those are y values between f of a and f of b. Where they're not the same, then there's a number c in the open interval ab such that f of c equals n. Well, that's what we're doing when we're looking for a 0 here. What we're seeing is that to the left here, and this is a x cubed, this is a polynomial. That's a nice function. That's continuous everywhere. Polynomials are continuous everywhere. Sine and cosine, continuous everywhere. So we have a lot of really nice functions we work with. We call those continuous functions. So we start with a continuous, and I said I was going to look between 0 and 2. So f of 0 I can see was a negative value, and f of 2 I can see is a positive value. So I should expect this to have every y value in between, in particular the 0. So that's how I use the intermediate value theorem to determine whether or not I have a 0. So there are several questions being asked here, and you can see they're doing a less than and greater than, the 0.8 and 0.9. So they're getting you to have an even smaller interval over which we're looking for the 0 on this function. Now a hole is called a removable discontinuity. So a hole is a place where you basically have a bead on a wire. The endpoints are not holes, those are endpoints. A hole would be a place on the graph where everything is nice except there's one little spot where there is no function value filling in along the graph. So at 3 and 5 here, this is discontinuous. It's got a function value somewhere down here. There aren't any units on here because the question didn't need units. So here it wants you to put a removable discontinuity at 3 and a jump discontinuity at 5. So the one I showed you has removable discontinuities both, so it can't be this graph. Some of the things in life around us we don't really consider as being continuous, like the temperature of a specific location as a function of time. Well, temperature is a continuous function, even though we typically only read 98.6 or 98.7 on a thermometer. Or the daily temperature, I'm not interested in the 5th decimal place for daily temperature, but it is continuous. So if you could put it on a number line, and every spot on the number line could be valid, even if we don't use it that way, then it is a continuous function. So here they're asking you to select all the ones that are continuous functions. We already looked at how you would evaluate a limit like this. F of 3 is 5 means that when I take this limit, when I put 3 in here, this part is going to be 5. G of 3 is what I'm wanting to find, so 3 times 5 is 15 minus g is going to be equal to 9 if this is continuous. So that goes back to our definition of continuous at a point. These can just be put in if it's continuous at a point. You can find the e to the x button here on your calculator. So if you wanted to graph this, you could do it as one full piecewise function, and using the methods that we did on the first test rather. Well, the chapter 1 test. Or you could just do these individually and take a look at the graphs. So it's up to you which way to do these. But it's easier to actually draw the graph. I just want to remind you that x goes to 1 minus means I'm going to 1 and looking to the left. X goes to 1 plus means I'm going to 1 and looking to the right. You can tell which one of these pieces is left and right. 1 minus would be the things below 1, which are the first graph. And 1 plus would be the things above 1, which would be the second graph. Number 11 asks you to locate the discontinuities. That's where you're going to have a hole in the graph or some other feature, a jump, vertical asymptote, or heavy oscillation. There's only one problem here because e is always a positive number, but for this one, 8 divided by x, there's one little problem there that should be really obvious to you. Can't have zeros in the denominator. Using continuity to evaluate the limit here, I could put this into my calculator to figure out what this is going to be. So parentheses 48 plus the square root of x, close parentheses, and I need to go out of the square root, close parentheses, divided by parentheses, and this is a whole square root, second square root of x. 48 plus x, rather. 48 plus x. Now I'm really doing a whole lot more work here than I need to for this problem. I forgot my division, so let me go back and put that in. Remember that there's a delete here, but there's also an insert above that delete. So I can insert my parentheses and my division, divided by parentheses, and I'd be able to graph this. But before I do that, note that I could do x goes to 1. There's no problem with continuity here. When I put this in, I get 48 plus 1 gives me 49. That's going to give me 7. And the square root of 1 is just 1, so 48 plus 1 would be 49 over 7, should give me 7. So let's see if that's true here. I'm going to graph this. I can't really tell. If I look at my table set, I'll start at 1. No, I'll start at 0. That's good. The second table, there really wasn't a problem at 1. This is defined there, so 7 would be the answer. So I did a whole lot more work here on purpose to show you that I could have just plugged this in. So it looked like it was difficult, but it really wasn't. Using continuity to evaluate here, continuity means if it's nice, this is around 1, this is nice. So if I put 1 in here, I end up with the answer pretty quickly. 14 and 15, they're wanting you to find the numbers for which f is discontinuous and determine whether f is continuous from the right or from the left or neither. So if we put 0 into the first one, we get 0 plus 8 is going to give me 8. If we put 0 into the second, we get e to the 0, which is 1. So it's definitely going to be discontinuous there. X plus 8 is a line, 5 minus x is a line, e to the x is a nice continuous function. So everything's nice except maybe at endpoints. We could try 1 in here, e to the first power is e, and then if we put in 1 in here, we got 5 minus 4, which is, and 5 minus 1, which is 4, and that is not e. So we know we also don't have a continuity there. We have some kind of jump in both of these. I'm going to go to paper to work number 15, and you should be able to work this one on the test. So it says f of x is equal to x squared minus 4 over x minus 2. And I'm interested in the limit here. I want to know what the limit is as x goes to 2 from the left. I'm not interested in the right side at all. X squared minus 4 over x minus 2. Now I could look at my graph and figure out what this is, but this factors pretty easily. So this is the limit as x goes to 2 from the left of x minus 2 times x plus 2 over x minus 2. Those go away. Now I can just plug in the 2, and I get that this is going to be 4. So there would be my function value. In order for this to not have a jump, because we want a and b so that there is no jump here, and this graph really only has a hole in it. So if I didn't have the second pieces, I'll be able to draw this graph as a line, x plus 2, and just put a hole when x equals 2. So if I put 2 in for the first one, it's 4. And I want, if I put 2 in for the second one, that would be a times 2 squared minus b times 2 plus 3. I want it also to be 4. So let's clean that up a little bit. We get 4a minus 2b plus 3. And we're going to move things around. So I have 4a minus 2b is equal to, taking 3 to the other side, would give me 1 here. So there's one equation. And the second one also has to match. So the second one here, the 3, the second endpoint, the interval here, has to be matching with the third equation in our system of, well, not our system, our piecewise function. So if I put 3 in for the second one, putting 3 in here, I get 9a minus 3b plus 3. I put 3 in for the second. I want those two to be equal because I want them to match at that piece. So intersecting is another way of thinking about it. At 3, if I was going to draw the whole thing. So if I put 3 in here, I get 6 minus a plus b. So this is 6 minus a plus b. Moving stuff around, I want the a's and b's on this side. So if I add a, I get 10a. So I'm adding a and I'm subtracting b minus 4b. And I'm subtracting 3 there is equal to 3. So I have two equations and two unknowns. 10a minus 4b is equal to 3. Now I can use what's called an augmented matrix to write the bare bones of this, and then we'll go to our calculator to solve it. We could do this by elimination, substitution, Cramer's rule. There's lots of ways to solve systems of equations like these. So I've got this system here. Match the pieces, put in the right numbers. So the bare bones would just be the coefficients. 4, -2, 1. A's and B's have to be in the same places, and the numbers have to be in the same places. And then we have 10, -4, 3. So I'm going to put this system in the calculator under matrix. So second matrix, you can see the word matrix there. I'm going to go over and edit, and I'm just going to use the first matrix. This is 2 rows by 3 columns, so it's 2 by, and you can see it opened up 2 rows. If I put 3 first, then I would have seen 3 and I could have gone and fixed that. So this is 2 by 3, and the one I give you on the test will also be. So now I'm just going to type the numbers in there. 4, enter, -2, make sure you're using the negative, 1. It goes straight across the row, just like I wrote them down. Straight across the rows. 10. So the A's and B's have to be on one side, and the numbers have to be on the right. They need to be on the right. So this is -4 and 3. Now once I'm done with this, I can quit out of here, and I want to go back and do what's called a row reduce echelon form to solve this. So it's just keystrokes. So I'm doing second matrix, scroll up, math I need, scroll up, second matrix math, scroll up to row reduce echelon form, 1, 2, 3, 4 for the B. And then I have to put the matrix A in here. So second matrix, and see A is right there, just hit enter. If I hit enter, it's going to give me the row reduced echelon form of the solution. So what I have is the solution to my A's and B's. So this is 1, 0, 0.5, 0, 1, 0.5. This is also an augmented matrix. So it has the coefficients. This says 1A plus no B's gives me 0.5. So that implies that A equals 0.5. This says 0 A's and 1 B is 0.5. So B is equal to 0.5. So this is what I would be looking for on the test. Number 16 is another intermediate value problem, so you're just going to work through the whole idea of the intermediate value there. And it says f is continuous, so we have to have continuity on it. It starts on a closed interval, and they've given you some numbers. And then we're looking for a y value. This capital N is a y value between f of a and f of b. So just think about the intermediate value theorem as you're going through that. On number 19, they use the absolute value of r is less than 8. And that actually means -8 is less than r is less than 8. One interpretation of the absolute value is that if it's the distance between 0 and the number here. So this is what r would be. The absolute value of r would be the distance. So one of the r's could be this way, but it also could be this way, -8. So r could be anything from -8 to 8, which is how we get that.